Alright, good afternoon. Any question before we start? So today I'm gonna go over some basic things on signal processing. So hopefully by end of this week or next week, Monday, we can start the 1 degree of freedom system free vibration. So let's start with oscillatory. As you know, this course is about oscillatory motions. So oscillatory motions can be categorized in two categories. The motion repeats itself regularly. So the motion is going to repeat itself regularly like the spring. So spring motion. So if you have a mass and a spring, it's at constant or at a stable position. If you move the spring, the mass and a spring, and then release that, it's gonna start oscillating. So this oscillatory motion is gonna repeat itself. It's gonna see here, then it's gonna see up there, then it's gonna back to this point, and it's continue if we don't have any friction. Or two, the motion can be irregular. Like the earthquake, the motion that you will see on earthquake. So then we can define the periodic motion. Motion repeats itself after equal interval of time. So in periodic motion, the motion is gonna repeat itself after equal interval of time. So for example, if this is time, if this is x, the location of the rigid body, so if we have something like this, x is going starting from 0, goes to after 1 second it's going to be at this point, and after another second it's going to be at the starting point, and then it's going to repeat itself and continue regularly. So we can write x of t, x at any point, it's going to be x at t plus this period of time is 2. So 2. So for example, if you pick here t1, x of t1, whatever is the x of t1, if you add t1 by 2 seconds, you end up to here, t1 plus 2 seconds. These two, they have the same magnitude of the x. So x of t1 it's going to be equal to x at t1 plus 2. And in general, we can say n times 2. Instead of having 1 period of time, I have 2 periods of time. Or 3 periods of time. In any case, t plus n times 2 is gonna have the same thing. So we call this, we represent that with a capital T, and we call it periods of time. Period of oscillation. Sorry. It's one term on periodic function is a capital T, which is period of oscillation. It says that x at any specific time is gonna be x at t plus n times period of oscillation, and n can be 1, 2, 3, and any other number. Good? In signal processing, we can define the frequency of oscillation. This is we represent by f, and it's 1 over t. So period of oscillation, it says how long it's gonna take to have one cycle. In this example, it's gonna be 2. So the period of oscillation is 2. The frequency of oscillation, it says how many oscillations do we have in 1 second? So it's 1 over t. In this case, we are gonna have half cycle for this example. So frequency of oscillation in this example is 0.5. Make sense? In 1 second, we are going to cover half cycle of motion. So this is the relation between frequency of oscillation and period of oscillation. Good? All right. Now let's talk about and the motion. I mean, the periodic motion can look like this. It can be so these are all three are periodic function because the motion repeats itself after equal interval of time. So in this example, if I ask you what would be period of oscillation, the answer is what is the period of oscillation for this? 8. It's not 4 because this is not the same as this. It's positive, it's negative, but entire of this is 1 cycle. Then after 8 seconds, you are gonna have the same motion. In this example, is 3. You will have you pick any point, add it to 3 or n times 3, you will get the same x. Make sense? So this is the definition of period of oscillation and frequency. So now the simplest type of periodic motion is called harmonic motion. So a harmonic motion make sure that you see the difference between them. The harmonic motion the simplest form of periodic motion. So what is the simplest form of periodic motion? It can be either sine function or cosine. If our function is something like this, a sine of omega t, then it's a periodic function. Why it's periodic function? Because it's gonna, the sine and cosine function, they are gonna repeat itself. This is A. This is the period of oscillation, because this is gonna repeat itself. Or cosine function. X of t would be b cosine of omega t. So this is b. This is period of oscillation because it's going to repeat itself after t. And this simplest form of periodic motion is called harmonic motion. Later on, we will look at harmonic analysis. In harmonic analysis, by applying the Fourier series, have you heard or have you seen the Fourier series? So we are gonna change the periodic motion to the harmonic motion. So for example, later on, if we have a motion like this, which is periodic but not harmonic, it's not harmonic because it's not sine or cosine. By implementing the harmonic analysis, we write a term or a summation of the function which all are harmonic functions. So with the summation of some sine and cosine function, we change this non-harmonic motion to the summation of harmonic motion. Why it's important? Because the harmonic motion, sine or cosine, we can differentiate them infinite times. There is no problem. The derivatives are simple. Derivative of sine is cosine. Derivative of cosine is negative sine. So for those reasons, we would like to deal with the harmonic motion. Good? So let me look at the harmonic motion for now. Suppose this is x-axis and this is y-axis, and this point, I mean point P or particle P or concentrated mass P is moving along this circular path at the angular velocity of omega. It's constant angular velocity. So when it's at the angle of theta, when this point P is at the angle of theta, if I ask you to write the term for the x component of point P, x component of point P is this, x of P is r cosine of theta. And y component of P is yp is r sine of theta. Whatever is the angle of theta, you can write the x component and y component of that. And theta is a function of angular velocity. Whatever is the angular velocity times multiplied by time, you will get that angle of theta. So I replace theta by this. I will get r cosine of omega t and r sine of omega t. So now x of point P as a function of time is varying with the cosine function of time. And y component of point P is a function of time, which is varying with the function of time. So it's a periodic motion. So for example, if we have a pin and this bar, it's a pin on a slot, so it's a scotch mechanism. So here, this we have some guide here. This part can move just vertically, so we have mass and a spring there. When this pin is rotating at the constant speed of omega, like this one, if I ask you what would be the motion of mass m, the motion of mass m is same as y components of position of point P, which is this. So it's a harmonic motion. This is one example to do that, and this is a sine function. For this, a sine of omega t. So this is gonna be, if this is a, it's gonna be a sine of omega t or r sine of omega t. Good? It's a harmonic motion. Can you tell me what would be the period of oscillation for any of this motion? What would be the t? For this? 2 pi? Okay. So you are saying that I can write r cosine of omega t equals to r cosine of omega times t plus 2 pi. Which is r cosine of omega t plus 2 pi omega. Can we say that? We cannot, because omega suppose is 0.1. 0.1 times 2 pi, you cannot say cosine of omega t plus 0.2 times pi equals to cosine of omega t. What we need to do is write this. R cosine of omega t must be equals to R cosine of omega, replace this t by t plus period of oscillation, which is capital T. And then, if you multiply this to R cosine of omega t plus omega times capital T, which is the period of oscillation. Then, as you said, omega t, if omega t is equals to 2 pi, 2 pi plus this, it's going to have the same value of the cosine of omega t. So, is that clear? So we can say the period of oscillation is 2 pi over omega. So whatever is the whatever is the omega and the harmonic motion, the period of oscillation is 2 pi divided by omega. If omega is 1, it's going to be 2 pi. But if you got different value for omega, you will get a different period of oscillation. And frequency is 1 over t, it's omega divided by 2 pi. And this is true for this as well as this. Sine and cosine, they are the same. For omega t, if it's 2 pi, you will get the same sine or cosine value. Okay. Now let me work on this. The cosine and sine both are harmonic motion. So I will work with cosine for now. I will back to the sine. I mean, it's going to be the same. It's not different. So if this is the displacement of point P in x direction, what would be the velocity of this motion? I should differentiate this with respect to time. R is constant, so only term is varying with time. Is changing with time. So derivative of cosine would be negative R derivative of this. It's going to be omega. R omega sine of omega t. So this is the velocity of point P. What would be the acceleration of point P? Why we are interested about acceleration? Because force is going to be mass times acceleration. We can figure out how much force is going to apply to the system if you have the acceleration. I should differentiate this one more time. This is constant, I'll keep it here. Derivative of sine of omega t is omega cosine of omega t. It's got negative R omega squared cosine of omega t. Good? So now, this is cosine, this is sine, negative sine. If I want to change negative sine to the cosine term, I can write negative R omega sine of omega t is positive R omega cosine of omega t plus pi over 2. Cosine of any angle plus 90 is going to be negative sine. You remember this. So now, if you compare these two, for example, at time 0, you will get R cosine of 0, but here you will get something times cosine of 0 plus 90. So the velocity leads displacement by 90 or pi over 2. We work with the radian angle. We don't use 90 degree here because everything is going to be in radian. It's the reason that I use pi over 2 and not 90 degrees. So velocity leads the displacement by pi over 2. Can you tell me, would you compare acceleration with displacement and tell me what can you say about the acceleration and displacement? Acceleration leads the displacement by how can I change negative cosine to positive cosine? Say it again. Pi. So it's going to be positive r omega squared cosine of omega t plus pi. So acceleration leads the displacement by pi. So let me define another term. Two harmonic motion are synchronous if both have the same, we call it frequency or period of oscillation. Frequency means F, but sometimes since this is representing omega, we call omega as a frequency. But we know that frequency is 1 over t, which is 1 over 2 pi over omega, omega over 2 pi. So sometimes we use term of frequency than omega. But we know that frequency is omega divided by 2 pi. So if we are given with two harmonic function motion, they are synchronous if they have the same frequency. For example, if x1 is 10 cosine of 2t and x2 is 5 sine, either sine of 2t minus 0.5. These two are synchronous because they have the same omega. Although this one has the other angle on the parentheses, but the frequency of these two is the same. So they are synchronous. Good? So let's see how good you are on harmonic functions. So you are given with two harmonic motion or harmonic function, and they are synchronous because the frequency or the omega for each motion is 10. We would like to know at which time x1 has its maximum value and at which time x2 has its own maximum value. number 7.
So cosine is maximum when it's 0, so I said x1 would have to be 0, or t1 would have to be 0,
Okay.
and then t2 would have to be 1/2.
5 over 10. Okay. Different idea. Okay, this is the cosine function. The maximum it occurs at 0 at time equals to 0 or time equals to 2 pi. So either set 10 times t equals to 0 or set it equals to 2 pi. So let's start with time 0. 10 times t equals to 0, t1 would be 0 divided by 10. As Brandon said, it's going to be 0. For this one, 10 times t2 minus 5 equals to 0. 5 goes to the other side. 10 times t2 equals to 5. t2 equals to 5 divided by 10, or 0.5. If you put at 2 pi as well, it's going to be 2 pi divided by 10. Set it 2 pi, it's going to be 2 pi 5 plus 2 pi. So if you divide by 10, t2 would be 5 over 10, 2 pi over 10. So if you compare these two, t1 with this, the time lag between these two is 5 over 10. This divided by 10. So we call this as a phase angle. So whatever is after omega times t, we call it phase angle. Negative. And we have a term on signal processing, time lag. Time lag is this is the time lag that we define. Good. This is the phase angle, whatever is this. Light is 5 divided by 10. It's going to be the time lag for this. So whenever whenever this guy is at its maximum, the second one, it's gonna be there. It's gonna be at the maximum 0.5 seconds later. So the time lag for this is 0.5, which can be get by dividing 5 by 10. So if this one is at time 0 is at the maximum, this one it's going to be at its maximum at time 0.5 seconds. All right. Any question about this? All right. Let's look at we are gonna represent the oscillatory motion, this guy, by using the complex number. Let's see how we can do this. For complex number, x-axis is representing the real parts, which is x or a in this case, and y-axis is representing the imaginary part, which is b. So the vector x can be represented by a plus I times b. This is how the imaginary numbers or complex numbers are working. So if x of t is r cosine of omega t, we can represent the position of point P by the complex number like this. Vector x is gonna be x of p plus I y of p by the complex number. X of p representing the x-axis. This is representing this one, and this one can be represented by e power I omega t. R e I omega t would be r cosine of omega t plus I sine of r sine of omega t. And this is x of p, this is y of p. So I can say that real parts of this complex number I represent it by RE. RE meaning real parts of e power I omega t is gonna be equals to x of t, and y of t, if I want to represent that, is gonna be the imaginary part of e power I omega. Good? Now, if I want to differentiate this with respect to time, I'll keep real parts here. Real parts of derivative of this with respect to time. Derivative of this, derivative of exponential function is going to be the same, and times the derivative of whatever we have up there with respect to time, which is I omega. Good? Everybody can see how I differentiate this. Derivative of this with respect to time is going to be the same function times derivative of this, which is I omega. So I omega e power I omega t would be I omega times cosine of omega t plus I sine of omega t. So this is I omega, and e power I omega t is r cosine of, not r, it doesn't have r at the back, it just has cosine of omega t plus I sine of omega. So if I multiply this, I will get I omega cosine of omega t plus I square means negative 1. So negative omega sine of omega t. So if I ask you what would be the real parts of this, you can look at this. This is the imaginary part. The real part is going to be negative omega sine of omega t. Negative r omega. I forgot. Where is the r? It's the r. I missed r on the back. So the real parts of this is going to be negative r omega sine of omega t, which is the term that we differentiate when we were working on velocity term. And derivative of velocity is going to be acceleration. So real part of Ri is constant, I don't differentiate that. I omega t, derivative of this is going to be I omega times e power I omega t. I times I is going to be I squared or negative 1. Real parts of negative are we have one omega here, omega squared. Omega squared e power I omega t. So Ri omega, I just wrote R omega I times I omega. These two is going to be omega squared. R times I squared is going to be negative R. Because I is a square root of negative 1. So what would be the real parts of this? Is going to be negative R omega squared cosine of omega t, which is same as this one. So, for example, if this is the axis of the vector of location for point P or point X, whatever, this is the theta, which is omega t. The velocity term is gonna lead the displacement by 90 degrees. So if you rotate it by 90 degrees, it's going to be velocity. And the acceleration is going to lead by 180 degrees from the displacement. So this is going to be the acceleration term. Any question on this? All right. This is another. This is a complex representation to represent the oscillatory motion. All right. Let me talk about adding. If we have any motion like this, x of t is x naught plus a sine of omega t plus b cosine of omega t. So this is the summation of two harmonic motion. So I can write x of t, x naught is a constant. X naught, xt minus x naught equals to a sine of omega t plus b cosine of omega t. I have summation of two harmonic motion with the same frequency. This is a synchronous motion. These two are synchronous. So I would like to write this as this one. A sine of omega t plus phi. Just summation of this harmonic function, this two harmonic motion. I would like to write it down as one single harmonic motion and deal with this one instead of having two harmonic motions. So I'm looking for A and phi. What should be the value of A and phi? So if I expand this, A sine of omega t cosine of phi plus A cosine of omega t sine of phi. If I expand this, it's going to be this one. Good? I just expanded. Sine of A plus B would be sine of A cosine of B plus cosine of A sine of B. I did the same thing. A sine of, this is A, this is B. A sine of omega t cosine of phi plus A cosine of omega t sine of phi. Now equate right side to A left side. So A here we have A sine of omega t. On this side we have capital A sine of omega t times cosine of phi. It tells me A must be equals to A sine of A cosine of phi. Right? A cosine of phi. If A cosine of phi equals to A, this part is going to be same as this. If B equals to A times sine of phi, we can have these two sides equals to each other. Now, in these two equations to unknown, I will solve for A and phi. So how can I solve for A? If I square them and add them up, I can find A would be s square root of A squared plus B squared. And if you divide this by this one, A sine of phi divided by A cosine of phi would be equals to B over A. B over A would be sine of phi divided by cosine. This is the tangent of phi. So phi would be tangent inverse of B over A. Tangent inverse of B over A, it's going to be phi. So you have phi, you have A, you can replace that single harmonic function with these two. Any question before we work on one example? Alright, let me work on one example. If you are given with two synchronous functions, you know what would be the synchronous function. There are two harmonic functions which they have same frequency, like this. So for example, if x1 of t is 10 cosine of omega t, and x2 of t is 15 cosine of omega t plus 2. And we have a motion, or we have a signal which is coming from adding of these two, x1 of t plus x2 of t. So 10 cosine of omega t plus 15 cosine of omega t plus 2. We would like to write this omega t omega t. We would like to write these two functions as a one harmonic function. I wrote as a sine function, you can write as a cosine function. It's sine and cosine function are 90-degree different from each other. Sine of x, it's going to be cosine of pi over 2 minus x. So cosine of x would be sine of x plus pi over 2. So if you want to deal with the cosine function, just subtract by pi over 2. Good? These two functions are synchronous because the frequency of both functions are the same, omega. So it means we should be able to have one single harmonic function which is representing the summation of these two. So let me show you how we can do that. First, we expand the second term, 10 cosine of omega t. If I expand this, it's going to be 15 cosine of omega t cosine of 2 cosine of a plus b, just to refresh. It's going to be cosine of a cosine of b minus sine of a sine of b. So cosine of omega t plus 2 is going to be cosine of omega t cosine of 2 minus sine of omega t sine of 2. The angles are in radians. Don't use as a degree. Here I have cosine of omega t, there I have cosine of omega t. So I can write 10 plus 15 cosine of 2 cosine of omega t minus 15 sine of 2 times sine of omega t. So 10 plus 15 cosine of 2, you can do math. Just find the cosine of 2 radian, this is radian, times 15 plus 10, you will get 3.76. And 15 times sine of 2 radian, you will get 13.64. So we will get negative 13.64 sine of omega t plus 3.76 cosine of omega t. And we would like to write this as a sine of omega t plus phi. Compare that problem with this. Here we had, on the right side we had A sine of omega t plus B. On the left side we had A sine of omega t plus B cosine of omega t. A sine of omega t, this is A, B cosine of omega. So the capital A, or the amplitude of this would be A squared plus B squared, which is a square root of negative 13.64 squared plus 3.76 squared. It's going to be 14.50. This is A, and phi would be the tangent inverse of B over A. B over A. B is this guy. This guy. 3.76 divided by negative 13.64. In degree, the angle would be 164.6 or 180 plus 164.6, which is 344.6. Which angle should be big? 164 or 344? Both angle gives us the same tangent, but one of them is the correct. Which one? Any idea? Tangent is sine divided by cosine. So E divided by I, sine divided by cosine. So this part has negative sign. And this is on the second quadrant, this is on the fourth quadrant. On the second quadrant, sine is positive, cosine is negative. And on the fourth quadrant, sine is negative, cosine is positive. Both are going to give me the same result. But the way that we have A and B, it's going to tell me the angle should be 160. And before we are done, you should change it to the radian, because when you want to represent this as a sine of phi omega t, it should have the radian angle. So A is 14.15 sine of omega t plus, this is gonna be 2.87 radian. So when you add two motion which both are harmonic and are synchronous, the summation of these two, it's going to end up to one harmonic function. and this is how we can find the amplitude A and the phase angle. The phi is the phase angle as we define. Any question about this? All right. Let's see if it's the last. Yeah, it's the last topic before we start. Free vibration of 1 degree of freedom is harmonic analysis. Harmonic analysis, if you remember, I said that they have harmonic motion, the simplest form of periodic function, which are sine and cosine functions. Now, in harmonic analysis, we are given with periodic function. It means the motion is gonna repeat itself over the time. So this motion is gonna repeat itself over the time. This is x or y, and this is the time. So it's a periodic function, but not harmonic. It's not harmonic because it's not sine or cosine. By doing the harmonic analysis, we are using the Fourier series. We are using the Fourier series and write this periodic function as a summation of infinite terms of sine and cosine function. So if this is x as a t, this is, suppose this x of t representing this function. One periodic function, but not harmonic. Why it's not harmonic? Because it's not sine or cosine. We would like to represent this as a summation of summation of infinite terms of cosine and sine. This is a1 cosine of omega 2, b1 sine of omega 2. Next term is a2 cosine of 2 omega t plus b2 sine of 2 omega t. And you continue. Third term a3 cosine of 3 omega t. And you continue up to an cosine of n omega t plus bn sine of n omega t. So if you represent the periodic function with the summation of harmonic function, we call this process, this analysis, as a harmonic analysis. What's the point of this? Dealing with this function is not easy. When you want to differentiate, to do other analysis, it's difficult to do that. But dealing with the sine and cosine function, it's much easier than the other non-harmonic function. So this is why in signal processing, they would like to do the harmonic analysis to get this one. So ideally, the number of terms should go to infinite terms, but in reality, we may need to consider first 3 terms, depending on the accuracy that we need. We may go up to 1 term, two terms or more or less. So, but mathematically we should go up to infinite number of terms. So can you tell me how can we get the omega from the original function? If this is my function 0, 5, 4, 8, 12, how can I get the omega? What's the period of oscillation on the original function? Can you tell me what is the period of oscillation? 4. It's gonna repeat itself after 4 seconds. In harmonic function, omega is, or t is 2 pi divided by omega. So if I'm looking for omega, omega would be 2 pi divided by 4 or pi over 2. So this omega right now is now. The harmonic analysis, in harmonic analysis, we're trying to find the coefficients. So the goal is finding A naught, which is a constant part, A1, B1, A2, B2 up to A and B. So if I rewrite this again, let me define the harmonic analysis. Harmonic analysis, in harmonic analysis, we are going to express x of t as infinite sum of sine and cosine terms. This is where you are gonna see the application of Fourier series. So Fourier series is applicable in signal processing by implementing the harmonic analysis. So x of t should be represented by a naught over 2 plus summation of n goes from 1 to infinite value. I'm writing this summation as a sigma. An cosine of n omega t plus bn sine of n omega t. The right side is called the Fourier series of the function of xt. So Fourier series is going to be right side of this expression. So if n equals to 1, n goes from 1. It's going to be a1 cosine of omega t, 1 omega t, plus b1 sine of omega t, plus n goes to 2. A2 cosine of 2 omega t, plus b2 sine of 2 omega t for 3, and it goes up to infinite values. And as I said, omega here is 2 pi divided by t. So on Wednesday class, we go over the harmonic analysis to find the value of A naught, A1 to AN, and B1 to BN. On homework 2, one of the problems is asking you to derive those terms.